And we're recording, so welcome back to System Solver. Yeah.
Where can you get like the new files for like my public?
So the grader will send this out today. He'll send these out. All right. So today we're continuing our lectures on compiler implementation. So last time we looked at how functions get emulated at the instruction level. And today we're going to show how to actually write a compiler that will generate assembly code that will give us this function behavior that we want out of our function. So any questions from last time about the behavior of functions, their semantics? How about the answer to the homework? So if we had a recursive version of factorial, how many stack frames would you have, or might you have, if you're computing factorial 10? Yeah.
12 or whatever calls the initial factorial function, and then factorial 10 to 0 as the individual.
Yeah. So if you, depending on how you implemented factorial, whether you test the base case as 1 or 0, you'll either have a call for F0 or a call for F1. But you'll have at least 10 calls for the factorial function, maybe 11 for factorial 0. And if you included main, that would be one of the stack frames. So yeah, that's exactly right. So just to illustrate the point that each call of the function has its own stack frame. And why is that? Why does every call, why do we, or what's the function behavior that we get out of doing that? Yeah.
Because like we freeze the callers running part, and then so we know where to go back once we're done with the new.
Yeah, that's exactly right. So each call is treated as its own independent instance of the function. And if we didn't do that, if we had local state for the function, but we shared state across them, this behavior of recursive calls just wouldn't work. Even multiple calls to the function wouldn't work as expected, where the semantics of functions that we expect and we learned in C is that each call to the function gives us a fresh local state for that function. All right, good. Other questions on the semantics of functions, C-style functions? All right, so let's look at how we can actually implement these kinds of functions in our compiler. So this is where stuff gets really kind of meta. You got to remember that we're not evaluating, we're not building the stack ourselves in the compiler, we're generating code that's going to build the stack. So I think I kind of already went over this, but what are functions? What's a definition of functions? Yeah.
Like a block of code that you can refer to with one, call.
Yeah, one you can name a computation. And there's all sorts of variations of functions. In C, you can name them, give the types of the input arguments and the output arguments, and you get this function local state behavior. So how do we implement this local state in C functions? Yeah.
You create a new stack frame.
Stack frames on every call. Okay, so we already kind of covered that. All right, so to actually implement this in the assembly level, there's lots and lots of ways you can do this. So you can arrange parameters and local variables. You can arrange these in all different ways. But in order to make sure that if you write a function that I can call it in my compiled version of the code, compilers and systems will standardize how the stack frame is laid out and how the call is made. These are called calling conventions, or the application binary interface. So the binary here is like machine code, and they're just conventions. There's nothing here you can reason about. There's no particular principles except that the conventions tell you what the stack frame layout is, where do parameters go, where do return addresses go, base pointers, local variables. They tell you how to do parameter passing and how to get the return value. So all implementations of this function local state, this stack-based function local state, will have these attributes. But how you actually do it is system and machine dependent, it turns out. So there's this helpful website, this OSDev website. If you actually want to go build your own operating system, this is a great resource that actually walks you through starting to run code on bare metal without a kernel, if you're really interested. But it overviews some of the various ABIs, application binary interfaces, that different systems have. So for instance, in the and so it depends on what operating system you're on and also what architecture you have. So if you're on an ARM, device, the names of the registers are different, and you may not have special purpose registers. So in the Microsoft world, there are, actually I didn't even look at what the little differences are. So in x86 32-bit, parameters are always passed on the stack, so there's no registers, but on System 5 and x86 64, as we talked about last time, there are registers that we pass parameters on. And why did we speculate that you might want to pass parameters via registers? Yeah, just higher performance. But just to illustrate this, this is a decision. This is a design decision. It's not written in stone where these parameters go. And you can see that in the Microsoft API, they use different registers for parameter passing. So this is really, really just a convention. You can see these are the kind of things that are in every convention, the return value parameter registers, et cetera. There's also this notion, we won't have to worry about this too much, I'll just give you the code for it. But there's also a convention about who saves registers. So when you make that call, your function may be using various other registers like RBX and R12 and all these. Your function needs these registers in order to run. And so there's a question about who freezes that state when you call a function. And there's just conventions on doing this. So scratch registers are ones where the caller cannot expect to have those saved, so the caller must save it. And there's ones where the caller can expect it to have it saved. So for instance, in the System 5 ABI, the one we're going to be using, the B register is expected to be saved by the callee. So you don't have to worry about too much. These are just conventions, just to decide who does what, whether it's the caller or the callee. And I'll give you the assembly code for doing this. So the main thing is we just have to make sure we preserve RBX. All right, so that's the application binary interface. Any questions on what an ABI is, what a calling convention is? So quick quiz, I386 System 5, what parameter registers are used in the calling convention? Yeah, none. Yeah, there's no parameter registers. We're going to be using this one, the System 5 x86 64 or AMD 64. ABI. This is the one that we're going to be using. But I'll give you all this information. You shouldn't have to, you don't have to know this. I think few programmers keep this in their mind when they're programming in C. But I'm just going to give you the assembly code for doing this. But I just want you to be aware that when you go to debug, you're going to have to be aware of what's happening at the machine level. Okay, so those are calling conventions in general. And this is a diagram from this web page that I showed last time describing the calling convention for x86 64, System 5 x86 64, which is what's used by Unix, many Unix style systems. Linux uses this, which is why we're using this on Eustace. And this is a diagram of what its calling convention looks like, the AMD 64 System 5 ABI. So in this calling convention, there are 6 parameter registers. So the first 6, actually I can show here is probably better. Here's a function that has 8 parameters. The first 6 parameters are passed via registers. So you can see here's parameters A through H, and you can see A, B, C, D, E, F, the first 6 parameters. The caller is expected to populate the registers with these parameters to make the call. And that's because the callee function, especially if it's generated by a different compiler or a different developer generated with the same compiler, you want to make sure that that function will be able to get the parameters that you send it. That's why you have this convention. So the callee will look to these registers for the first 6 parameters, and then the rest of the parameters will be pushed onto the stack. So in the, I don't know if you remember this from computer organization, but by convention, the stack grows downward, heap grows upward, stack grows downward. Did you all learn this? Stack goes down, heap grows up. Okay, more or less. So what makes this, what also is a little confusing, what you have to keep in mind, is that when you push something onto the stack, so this is the current stack before we make the call. This brown section here is the caller's stack frame, is in there somewhere. When we push, we're actually subtracting an address. We're actually subtracting an address from the stack pointer. So the stack pointer, RSP, SP is for stack pointer, that's a register that holds a pointer to the memory location that is the top of the stack. And when you push onto the stack, all that happens is a move moves whatever data you're pushing onto the stack into that address, into the next address into the stack, and then decrements. Actually, it might decrement first, and then looking at this, it looks like it decrements first, and then copies the data onto the stack at that new address. With me so far on this? Does that make sense? And you'll get a really good crash course in what pointers actually do at the machine level when you're using C. So these registers like RSP, they're just registers. They just hold numeric binary data. But what they mean to the instruction set is a pointer. They're meant to hold the address in memory of the top of the stack. But yeah, just keep in mind that you've got the stack growing downwards. Whenever you push, the memory address of the top of the stack goes down. It's subtracted. Okay, so the caller in green, the one who's calling this function, myfunc, passes the first 6 parameters, copies them into these registers. Remember, this is just a convention. And then any subsequent parameters get pushed onto the stack. So here we've got H and G being pushed. And then the caller will use the call instruction. If you remember last time, all the call instruction does is it takes the current instruction pointer, that's the address of the current line of code that you're executing, and it pushes the next line of code. So that's the code, that's how we freeze the state, part of the state of the caller. This is the next address that you're going to execute in the calling function, the caller function. So this address gets saved onto the stack so that later, so why is that saved onto the stack? Why do we save the return address onto the stack when we make the call? Yeah. What was that?
So you can like go back.
Yeah, so you can jump back to it. So you can branch back to the calling function. So if we have main calling myfunc, in order to freeze the state of main, we want to save its stack frame, but we also want to know where to continue executing in main. And that address, that instruction pointer, that address that contains the next instruction in the main function, that gets pushed onto the stack next. And that gets done for you when you use the call instruction in x86. So that gets pushed onto the stack. And as soon as you do call, pushes the address onto the stack and then branches to the myfunc code. So here in light blue, this is where the myfunc side of the calling convention starts happening. This is where the epilogue of the function starts running. So the first thing it does, go ahead.
How would my phone be able to access G if it's hidden behind H?
That's a good question. So, any guesses on how myfunc will be able to access? Well, how can it access? Say, so ZZ is a local variable for myfunc. So how can it access ZZ? Yeah.
Why can't we stack for it at 20 different stack values backwards and then go backwards?
Yeah, so you can do some pointer, what you might call pointer arithmetic in C. You take this address of the base pointer, which is a pointer to the current stack frame, and you just add and subtract the amount that will get you to that variable. But the question is, this is not happening at compile time, right? How does the compiler know how far to go from the stack frame in order to find those variables? Or can we know? Yeah.
Well, when we assign a data type to every variable, then we know how much that, because every long is about 8 bytes, right? So if we know the data type of the variable and the long, then you can just subtract where we are from there or add 8 bytes, because that's how long long is. So you go there and then you go until you find the variable.
That's exactly right. So if you didn't hear your colleague, we know at compile time because the developer has told us the data types, and because these data types have a well-defined precision, I mean it's machine dependent, but it's well-defined, we can compute at compile time. We know exactly how much, and because the compiler is the one that is generating these push instructions, the compiler knows exactly how far away, at least from this base pointer, at least from this, once it has this address of the stack frame, it knows exactly how far away each of these variables is going to be. And that's actually the key, is that because you're the compiler writer, and so you're the one generating code that's going to be pushing onto the stack. And so you're going to generate code that, you know the first 6 are going to go to registers, so you'll generate code to move those into a register. And then you're going to generate 2 pushes, one for H and one for G. And because you as the compiler writer wrote code to generate that, you know exactly how many parameters there are going to be, you can actually at compile time compute exactly the offset of those variables in memory. Questions on that? Does that make sense? So yeah, very good. That's exactly right. This is what you can determine at compile time. Yeah.
Is this like the upper level of the kernel and the lowest level, kind of where it would cross over?
This is not the kernel boundary. That's a good question. So this is a boundary between two user space functions. The kernel boundary works a little bit differently, the way the calling convention works, because you have to go into a different processor mode. It's done a little differently. You trigger an interrupt. Take an operating system course to learn about this, but you trigger an interrupt, which causes it's basically an event that causes a kernel process to start running, and there's different ways to pass data back and forth between the kernel and user space. There are something they're called stubs, wrappers in C, which are used for the system calls, but then there is a different process for transferring control between the two. But yeah, this is just between two user space applications, like when you call printf or you call a library function. This is the calling convention that gets used, because both of those are operating in user space when you call library functions. So system calls versus library functions. System call transition to the kernel. Library functions like printf, fread, these are user space calls. In them, they may call the kernel, but when you call them from your C program, they're being called with this convention. So that's a good question. Yeah.
What about stuff like read or?
It depends on whether it's a system call or a library call. I can't remember. It depends on the man page they're in. I think the directory ones are actually library calls that call the syscall. The man page actually says don't use this. Like it recommends against using the syscalls for directories. What's that? It's the same thing. I think all the dear ones. So if it's man 3, that's a library call. Man 2 are system calls. And so the ones that are going to have a special stub function that then will transfer control to the kernel. The library ones are user space. So they're just like when you write your own C function, user space to user space C function, which uses this convention. Yeah, do you have a question?
Yeah, so regarding offsets, you said that, that makes sense, like if you know the width of everything that you're storing, but where is it actually storing that table of all the offsets?
That's a good question. So, so how can we do this? So if at compile time we compute these offsets, so the compiler will have this information, right? You can store this, the Python program, the actual running compiler program can compute all these offsets, but there's no table here that says what the offsets are. So how can we, I'll ask you, since you answered so well before, can you think how the compiler can ensure that the right offset is used at compile time? This is a little bit of a trickier question. I don't want to put you on the spot, but if anyone wants to answer, yeah. If anyone wants.
I can take a guess, but I think it's mostly because, or it can figure out because it's like an array, right? So if you think of it as an array, you can probably.
Yeah, I mean, that's a good start. So actually, one way to think of this is that since these are fixed constants, and also remember that XX, these variables, they don't have any meaning at the machine level. Remember, these are like ASCII symbols. So what actually happens is the compiler translates this symbol into just an offset. And so whenever you have an operation, and we'll talk about this next week, whenever there's an operation on a variable, an assignment or a use, it's not like the assembly is generating a label, because labels are for like branching. It's actually just going to generate a code that will hard code this offset. So this, like, whenever there's an assignment to XX, the compiler is going to translate that to an assignment to RB minus 8. And so there's actually a special instruction in the Intel world that will do this, like a single instruction that will let you do this computation. It's called register indirect offset addressing or something like that. So, RISC instruction sets don't necessarily have this, but sys complex, instruction sets, whatever they're called, have these actual helper instructions that are designed for making it easier to write compilers with fewer instructions. And so, yeah, that's a really good question. But it all comes down to the fact that what we can compute at compile time. We can compute at compile time what these offsets will be, and then our compiler knows that, so when it does the translation, it will exploit that knowledge in order to generate code that will behave like the original C program. Did you have a question?
About like fuzzing.
Related to this?
So like the stack frame. How do they count the stack frame?
How do you count the stack frame? So that, like, you mean the homework question?
Yeah.
So the homework question, so we talked about that before. So what was, how did we count the stack frames for the homework question?
Number of function calls.
Yeah, number of function calls. One stack frame per function call. So if you factorial 10, you have 10 function calls plus F0 in main.
Yes.
Okay, so that's how the compiler knows, because the compiler is the one generating the code. It can exploit whatever knowledge it has about the code in order to do its generation. Okay, yeah.
Really quick question. What happens if we do recursion with let's say we have, like, going back to the factorial function, would the offset be the same for the x value? Or would
That's a good question. So what I didn't quite talk about yet is that these are offsets from the base pointer, and those offsets are fixed for every call to the function because the function has a fixed number of parameters which all have fixed bit width. The question though is, how do we know so these are relative to this RBP pointer, how do we know what the RBP pointer should be? So the next question is, how do we make sure that this pointer is correct, that it's pointing in the right spot? And that's actually that's the first thing that the callee does, the function being called does. So after the call will push the return address so that we can unfreeze the instruction pointer, and then branch to myfunc. The very first thing myfunc does, by convention, is it saves the old RBP. So the old base pointer is up here. So remember, the base pointer, the kind of invariant, or the thing that the compiler wants to make sure is maintained throughout execution, is that the base pointer always points to the current stack frame. And so this is, again, where we have these special purpose registers that can help compiler writers. But the key is that you want to save one register to always point to whatever the current stack frame is. Now, it's easy now, if you have that done, then, and you know that the offsets are always fixed, then you're done, right? You just say whatever the base pointer is, use a fixed offset from the base pointer to get to the locals and parameters, as long as you know that RBP is always pointing at the current stack frame. So then the trick is, how do you make sure that RBP is always pointing to the current stack frame? And so the way that's done is you take whatever the old one is, assuming the old one is correct, you push that onto the stack. And why would we want to push that onto the stack? Yeah.
it means we jump back to it?
Exactly, so we can recover the caller's stack frame. So this is very much like recursive reasoning, where you have a base case and then you have a recursive case. The recursive case here is that we assume the current base pointer is the caller, and then we push it onto the stack. So that will guarantee that when you pop, you'll have the caller's base pointer. And so to make sure that we're at the current base pointer, we just by convention save whatever the current stack pointer is to be the base pointer. So, yeah, okay. I'll show it here. I'll show this example. I'll show another example again with another. I'll do it on a whiteboard, but just to get through this. So before we call the function, the stack pointer is here, and then we push the locals. Stack pointer's here. We make the call. Stack pointer's here. Okay, RSP. Stack pointer's here, where I'm waving the arrow. When we save the old base pointer, the stack pointer is here. So to set the new base pointer for the new function call, we just say, okay, whatever the current stack pointer is, we just copy that into the base pointer. So by convention, the base pointer will be pointing to kind of the middle of the stack frame, just because of how it's constructed and when you set the base pointer. It's just a convention, but just remember that right after the function is called, saves the old base pointer, and then sets whatever the current top of the stack is, which is like halfway through the construction of the stack frame. It just says, well, okay, whatever my current stack pointer is, copy that to the base pointer. Does that make sense? You see what I mean? Let me show this in a diagram before I move on. I want to make sure this is clear. Yeah, and I'll show this more later with a fuller example. But let's say I already have a stack frame here, and RBP is already pointing to the middle of my stack frame. So this is my stack frame for main. And then when I go to make the call, I push locals, or I push parameters, sorry, I push parameters. And then I push the old RBP. So whatever this address is, let's say it's like, let's just number these addresses. I take whatever the old base pointer is, it's pointing to address 1, and I save it here. I save it, so here's my locals. This is some local. And then when I transfer control, and then, oh yeah, there's the return address. And then when I transfer control to the callee, first thing I do is I push the old base pointer. I push the old base pointer. And what's the address of the old base pointer? Address 1. So I push that value here. And so, but now I'm running my current function, but my base pointer is pointing to main stack frame. So how do I make sure, oh yeah, so what I also forgot to mention here is that my stack pointer is pointing here, because this is the last thing I pushed. So my stack pointer was here, push. Stack pointer is now pointing at this memory location that holds the old base pointer, because that's what I just pushed. So then what do I do to update the base pointer to be my current function? Yeah. Yeah, exactly right. So I copy 7 into the base pointer, and so what that does conceptually is it makes the base pointer point to this memory address. Does that make sense? So yeah, literally RBP will hold the address 7. RSP holds address 7. This old RBP held address 1. And so now my RBP is no longer address 1, RBP is 7, which is pointing here. Does that make sense? Does that make it clearer? And then I go on, and then I continue constructing my stack frame inside of my call, which consists of allocating space for local variables. Sorry, these were parameters, which are also local variables. And so once I'm done that, I now have my stack frame for my callee. And this RSP gets pushed to whatever the top of the stack is. And so now I've got this, my machine is set up to where the base pointer is pointing to my current stack frame. And of course my stack pointer is at the top of the stack. Yeah.
So is this how programming language compilers cache, or print out stack traces?
Mm-hmm. Yes, exactly right. So a stack trace would follow, and there's other debugging information that goes in. But yeah, and so so when we go back to return to the caller, we can tear down this stack, and then we have an address to the old base pointer, so we can update our old base pointer. But if you notice what this does, if I had a new function call inside of my func, the base pointer would then be updated here, and it would be address 7, the old base pointer, the caller's base pointer. And so notice that if you look at this stack, I'm going to put this here. What these base pointers do is they create a chain of pointers that if you just follow the base pointer back down the stack without any offsets, you can just immediately trace the entire stack of base pointers by just following. Sometimes this is called the, I think, dynamic linkage or something, static linkage. The Dragon book has a different term for this. But if you could just follow the base pointers, you'll see the whole chain of function calls. And you could certainly use this to unroll the stack with additional debugging information about the function that's being called. But yeah, this is like the stack trace is the set of function calls that you have on the stack. Yeah, it's a good question. All right, other questions on the base point? Yeah.
Can you draw where the function parameters for my func are implemented into this diagram?
The function parameters?
Yeah.
So yeah, sorry, I call these locals. So the parameters are here. And they're also, where else are they in the System 5 x86 64? Yeah, in registers. Yeah, so this is just the convention of System 5 x86 64. The first 6 parameters are copied to registers first, and then the remaining parameters are pushed onto the stack. Just the convention. You can imagine doing this in very, very different ways. You could push all the parameters on the stack, and that's probably easier to write a compiler for. All right, questions on managing the stack or how this calling convention works? So we've got two special purpose registers in the Intel world, RBP for base pointer, RSP for stack pointer, and then RIP for instruction pointer. But you don't have to manage that yourself. It gets managed by the call and return instructions. All right, so the stuff in green, is it the caller or the callee that pushes this data? Yeah. Caller, good. And then the stuff in blue? Callee, yeah. And so they both work together in order to construct the full stack frame for the myfunc function. So that might be a little counterintuitive. You would think.
The stuff called the caller.
What's that?
The stuff called the caller, the green stuff or the brown?
The green stuff is the part. So this stack frame, this whole stack frame is for myfunc, but half of the stack frame or part of the stack frame is constructed by the caller because the caller knows the values of parameters. It also knows the return address. And the second half of it is set up by the callee because it knows its own base pointer, and it knows the previous base pointer, its own base pointer, and it knows its locals values. All right, yeah, go ahead.
Just to be sure, RSP contains the location of the stack pointer?
Yeah, RSP is the stack pointer, in other words, the top of the stack. Now, it's just a pointer, so when you pop from the stack, the data is not deleted or anything. It's just, by convention, this is the current top of the stack. But if you call push again, it's going to overwrite whatever data you had on there. Yeah?
How did the return address? Did it explain that part of it?
Yeah, sure. So the return address, so what's the return address? Where does this point to? Yeah.
Caller?
This is the caller's next instruction. So this is telling you, so when main is running, so main is a sequence of assembly instructions, and you have a call instruction, which I'll show an example of this soon. And then when you want to resume main, you have to resume it after the function call for our function semantics. You like in factorial, when you call factorial, you pause the parent call and call the child, and when that's done, you return exactly to the space where you just left off factorial. So this return address is the address in memory of the next instruction in the caller. So this is how you will be able to continue executing the caller function by going back to this address. And this is managed for you by the call and return instructions. Call will both put the return address on the stack for you and also jump to the function address. And return will pop that address off, whatever it is on top of the stack, and will branch to that call. And so has anyone ever heard of stack overflow attacks or buffer overflow attacks? Probably heard of these. So the crux of this is there are operations in C that if you have a buffer overflow, like let's say XX is a string, or it was easy as a string, what direction do you know what direction arrays go in memory? Are they positive in memory number or negative? They're positive, yeah, they're positive offsets. So if ZZ is a string, and it's only meant to hold 3 slots in memory, and you give it 10 slots, you can actually end up overwriting the RBP and the return address. And that's what a stack smashing attack does, is the attacker will exploit a buffer overflow in a C program, a buffer overwrite in a C program in order to blow away the return address, and then through some very clever tricks, they can attempt to replace that return address, not with some random place in memory, which will cause the processor to say, well, I likely will not be able to interpret these instructions, but instead to jump to an address that's under the attacker's control. That's some code that the attacker controlled. And so the classic way is to not only overwrite the return address, but also overwrite the stack with instructions, with assembly instructions, and try to get the return address to jump back to the code that the user passed as input, and then take control of the machine, execute shellcode. So this understanding these calling conventions will help you understand probably one of the most classic and prolific software security attacks like ever in computing history. The classic stack smashing attack, and it all comes from this calling convention. Now there's defenses against this these days. So the original version of the stack smashing attack I've showed it in class before. I probably won't have time this time as like special. You can see like a past lecture. You have to turn off a couple of protections in order to actually get it to work. But you can get it to work on your own machine and use it to do like privilege escalation or get shellcode running. All right, any questions on the calling convention? Any more questions on the calling convention? Hopefully we're all good on this. So, use this diagram. This is from this guy's website. I think it's a really good diagram. Use OSDev. Whenever you need a reminder, you don't have to keep this in your head. Yeah.
Can you just remind us one more time what's a prologue and an epilogue?
Okay. So let me get into that. Let me get into that next. So yeah, I'll show this exactly with an example. So here is a complete assembly program for, what function is this? A main function. So let me go through each piece of this. So these dot prefixed assembly instructions, these are called pseudo-ops. They don't correspond to machine code instructions. These are for various metadata about the assembly program, like in this case, what the name of the source file was. There's other properties of the binary that you want to set. Don't worry about these. I've given these to you. I've given you code to generate these. This text is saying we're in the text segment, which is where the program code goes in a binary. These are more pseudo-ops for describing a function. You don't have to worry about those. I also give you these. You just have to generate these. And then a function is really nothing more than just a label, an address in memory. That's really all a function is at the assembly level. And so in assembly code, you can name a label. You don't have to give an actual memory address. Okay, so this is the metadata for the assembly file, and this is how you declare, so to speak, a function in assembly. You just use these pseudo-ops here and then give a label for the. So when you did MIPS, did you have labels for branches?
Yeah.
Okay, so it's normal. Okay, so you're all familiar with this, yeah.
When I took CDA, NIPS was very poorly explained.
Okay, so yeah, and we'll see it when we do a call, but. Kind of at the machine level, you're branching to an address, but the assembler will allow you to name addresses. And actually, because the code, because remember we talked about linking, the address of the actual function may differ in the final executable file and in memory. So the assembler and the linker will handle this for you by using relative addressing. So at the assembler level, you just have to give a name to a location in the source code for branching. Yeah.
So are you using some MIPS into CodeGen or?
No, we're not using MIPS. We're generating x86-64. So this is all x86-64 assembly code.
Oh.
So I just asked MIPS because that's what you learn in computer organization. All right, so here's the prologue. This is what the prologue looks like for our simple main function. So recall, what does the prologue have to? So the prologue of the function, is that the green section of the stack or the blue section of the stack? It's the blue section. Because remember, the caller sets up this part, the first part of the stack. The callee sets up the remainder of the stack. So when the function, when the callee gets called, this is the first code. So if main is getting called, this is the first code that gets run when you call main. So the caller, the code for doing this is what the function call does. The function definition is the callee code. Does that make sense? I'll show a full example with like a function call as well, and you'll see why that's the case. But so a little trick question: the callee, its prologue sets up the rest of the stack, because that's the code that first starts executing when you do the transfer of control to the function. Yeah.
So, but also the metadata and the function label, that's done by the caller, correct?
Done by the what?
The caller function?
This metadata.
Yeah.
Well, technically this is done. This is the so-called compilation unit. In C, a compilation unit, think of it as one like assembly file or one object file, can have multiple functions in it. In my simple IR that I've given you, there's one function per compilation unit, one function per assembly file. So in this language, yeah, there's one function per file. But in C in general, no, you can have multiple functions in the same file. So this is just setting up a single assembly file and a single object file. And this is setting up a single function. So you could have more than one of these.
I was asking, like, is the metadata and the label
No. So remember, this is the output program that the compiler generates. So this is literally the assembly file that will get produced by your compiler. So this is not runtime. Yeah. So this is the main thing to wrap your head around. This is not runtime. This is compile time. This is the program that gets generated, and then these instructions are not being run yet. Once you assemble and link and run the assembly file, these will get executed. But yeah, this is the main trick to wrap your head around, is that this is not the stack creation. This is code that creates the stack. It's not literally the stack itself. Yeah.
Where's RBX and like RSP, RBP on the stack? I didn't see it.
So these are registers. Yeah. I probably failed to make that clear. This is called the AT&T syntax for assembly. There are at least two syntaxes for Intel assembly. In the AT&T assembly syntax world, so I mean, you learned computer org, right? There are registers. There's a finite number of those that the processor can access to copy and move data from, and then there's like main memory. In the assembly code, in the AT&T syntax, you can refer to these registers by their name, prefixed with a %sign. So whenever you see %sign something, that's a register name. That's one of the registers in the Intel world. So RBX is a register. And, also I probably didn't make it clear either that the first, on every line of an instruction, a real assembly operation, you have a mnemonic, the name of the assembly instruction that you'd like to run, followed by its arguments. So this is a push instruction for pushing onto the stack. This is a move instruction for moving. In the Intel world, there's like a lot of different variations of move. This is moving data between two, what are these arguments here? The registers, and another push instruction. Another peculiarity of the AT&T syntax is that the destination register is on the right. So this is moving whatever is in the stack pointer to the base pointer. You might see Intel syntax, which swaps them, which makes things just ultra confusing. But this is the destination. Remember, in AT&T, destination on the right. Okay, so this is the code that's going to be generated for a main function. So this is just a static assembly file. And at runtime, when you call main, when the processor executes the instruction of main, it will start constructing the stack. Okay, so here's the prologue. And so recall what the prologue of the function does. So the caller sets up the parameters and the return address, and then transfers control to the callee. And this is a callee like main, and these are the first instructions that run when it's called. So after calling, so this green stuff is the caller. Once it transfers control, it's literally branching to this label. It's branching to the address that's represented to this label and starting to execute code. That's why the first part of the callee function is setting up the rest of the stack frame. So caller has its own code. When it does a call, it sets up part of the stack, transfers control to the function, just jumps to the label, and the first part of a function sets up the rest of the stack. Questions on that so far? Okay, so remember what we need to do to construct the rest of the stack according to this calling convention. What's the first thing we do in blue at the callee? What's the first thing we do?
Save your return address.
Well, return address is saved by the call function. That's done by the callee, so it's in green. That's why it's in green. So it's for yeah.
Basically, the base staff is the base point.
Yeah. So we first save the old base pointer. So remember in our diagram here, the base pointer was pointing at whatever the caller was, whatever its base pointer was. And the first thing we do is to push the old base pointer onto the stack. So when we call push RBP, that takes the old base pointer and pushes it onto the stack. So the second thing we do, so the base pointer, if you remember in this example, the base pointer, after you push it, the base pointer is still pointing to the parent's stack frame. So the next thing we do is we want to update the base pointer to its new address, and that address, how do we know what the new address of the new stack frame is? well, so okay, so I had done more. Let me put this back into the state of the call. So we make the call, RBP is pointing here. RSP is pointing here. And when I push RBP, yeah, you have
You would use the stack pointer.
exactly, we use the stack pointer. So we push the old RBP, which is 1. And when you push, the stack pointer is updated to whatever the top of the stack, the new top of the stack is. So in order to get the new base pointer, we just copy whatever the current stack pointer is into the base pointer. Whatever the address of the current stack pointer is, we copy it into the base pointer. Questions on that? Does that make sense? So that's what these instructions do. We push the old base pointer, and then we move or copy whatever the RSP is to the destination register, which is RBP. And so at this point, our stack and our registers look like this. RSP and RBP are pointing to the same spot. The contents, remember, RBP is an address. This contains address 7. And the contents of it are whatever the old RBP was. The old RBP was address 1. So, I don't know, I think this makes pointers a little bit easier to think about because a register contains an address, and that's definitely not data that's on the stack. When you copy data from an address from a register onto the stack, if that data in the register was an address, then you've pushed a pointer onto the stack. So that's why this old RBP is conceptually a pointer to the old stack frame because it just contains an address that was the RBP previously. Okay, questions so far? Yeah.
On the code, what's the difference with the push Q and just normal push?
Yeah, that's a really good question. This is the bit width of the. I can't remember why I did this for the stack. I think because I wanted the stack to have a specific bit width to it, but it should be able to be inferred from the arguments. The assembler will infer the bit width of the argument. So basically, there's a move instruction for almost every bit width. You can move just 8 bytes or maybe 16 bytes, 32 bytes, bits rather. And so there are different instructions for those. If there's sort of a data type, so RSP refers to the 64-bit registers, but on x86, ESP will refer to the same register, but only the first lower 32 bits of it. So don't worry too much about this, details of Intel that also I'm not super familiar with. I just kind of worked it out. But Q, I think, is the 64-bit one. But even here, I didn't even put the Q, I think, because it will infer it from the assembler will infer it from the width of the register. Okay, so there's the prologue. We save the old base pointer. We update the new base pointer by copying this whatever the stack pointer is, which is pointing to the new stack frame. And then why do we push RBX? What's the point of this? This is a super subtle question if you were paying attention very, very closely before. These are registers that, according to the calling convention, the callee is supposed to save. Yeah?
Would it be to launch an instruction and save a variable?
Would it be, say again? Oh, sort of. So if the caller, so in the compiler world, it's easier to think of variables as being associated with memory locations, kind of like they have H and G here. But when you're doing computation, you have to move some of that data into registers to do operations, even in the Intel world for some operations. And so typically the compiler uses registers as a kind of optimization for operating on variables. And so what compilers will tend to do is they'll try to keep variables in registers for as long as possible. So if you have a program with 1,000 variables in a function, you only have, say, 32 registers, well, you won't be able to hold all variables in registers at all times. This is called the register allocation problem. So you'll need to swap in and out variable data into registers while you're executing the code. If you happen to call a function during that process, well, that complicates things even more because the function is doing its own register allocation. So the conventions just define which registers are callee saved and caller saved. Scratch registers are ones that the callee is allowed to blow away. Preserved registers are ones that the callee is not allowed to blow away, basically. So it's just by convention. You could have a convention that says the caller must always save all registers itself by pushing them on the stack, or however it wants to save them, or putting them back into memory. But this is the current calling convention, that some are allowed to be overwritten by the function that's being called, and some must be saved. So ESP and EBP are, of course, ones that must be saved, right? You don't want to blow that away for the caller, because then you'll lose the base pointer, you'll lose the stack pointer. EBX is by convention, and I can't remember what these are for, actually. These are like index registers or something, or segment registers or something like that. Does that kind of answer your question? So the registers are not one-to-one mapped to variables necessarily, but yeah, you could think that you could think of it in that terms, that if the caller had associated variable x with register EBX or RBX, then when it makes a call, this convention says the callee must restore the value of RBX when it returns. So yeah, you could think of it in that. You could think of it kind of in that sense. Is there another question over here? All right. So I feel like people are getting this. This is one of the more intricate parts of understanding compilers. So somewhat getting it. All right. So here's our prologue. So this is what the prologue code looks like. And just remember, this is code that's generated by the compiler. The compiler is not generating this. The compiler is generating code that generates the stack frame. That's the confusing part about compilers. Your compiler is not figuring out what the whole set of stack frames is going to be, like the stack trace for the program. All it has to do is reason about an individual function's stack frame construction and destruction. It's very much like recursive reasoning, where because each function is guaranteeing that RBP will always point to the current stack frame, you can ensure that recursive applications of that function will be correct. Same thing in factorial. When you write the recursive step of factorial, you can write it before factorial is written. That's the kind of confusing part about recursion, is that the way you make it work is that you just assume first factorial is written correctly. Just like in math. I think you learned this in discrete, if you have taken discrete, right? You write in your recursive step, you make the assumption that the recursive function is already correct when you write the proof of it, or when you write the program. Induction, yeah, exactly. When you do induction, when you do an inductive proof of a recursive program or a recursive function, it's the same as in recursion. You write the inductive step as saying, I'm going to assume that f is correct. I'm going to assume that it's correct. And it's the same thing here. I'm going to assume that RBP is correctly managed by the caller. And the caller also assumes that the callee correctly manages RBP. And because of that invariant, because of that assumption that every function makes, you can guarantee that your stack frame will be correctly constructed no matter what your recursive calls are, no matter what order the functions are called in. So that's a little bit more of a mathy way of explaining it. But that's the main trick of compilers, is that you generate code that preserves invariance, that preserves the behavior of the input program, and also preserves the semantics of how you implement it, preserves the behavior of the assembly program. All right, so that's the prologue. But for the first CodeGen project, there's no parameters. Parameters make things a little more complicated, so you won't have to support parameters. This is all the function call looks like for calling func from main. It's literally just the call op in assembly and then the label of the function you're calling. And so recall that the call function, all right, so to make this even a little bit more confusing, that prologue constructed the main's stack frame. But when we make the call, so this is main, when we make the call, we start constructing the callee's stack frame. Because remember, the caller, main, starts constructing the first half of the stack frame of my func. So what does call do? Call, so remember, anyone remember what call does, the call instruction does? Yeah. But it does jump to a label, but it does something else.
It saves
It saves, yeah, exactly. It saves the return address first. So yeah, I'm sort of jumping ahead to the full example. So this is main's stack frame. This is func's stack frame. So when main gets called, whatever its caller is, which in the case of like kind of a Unix world would be start. So this is the kind of caller part of the stack frame. This is the callee part. So when main gets called, the caller puts the return address on the stack and then does the branch, jumps to main. And that's when main takes over and starts constructing its part of the, oops. Oops, this skipped ahead. So after main gets called, that's when main starts constructing its the rest of the stack pointer. So this is the old RBP. And then when main calls a function, the first thing it does is it sets up the stack frame. So if there's no parameters, what does it do to set up the stack frame? What does the caller have to do to set the stack frame? Except for parameters, if there's no parameters, what does it need to do? Just the return address, yeah. So that's what the call instruction does. The call instruction first pushes the return address and then transfers control to func. Func also has a prologue that does the exact same thing. Oh, I'm sorry, the return address is not here. The return address is inside of the function's stack frame. And when you transfer control to the function, the func, what's the first thing it does when it gets called? Second. Right, does the prologue. What's the first thing in the prologue? Yeah. Base pointer. So the first thing it does, so this is the caller part, and then the callee part. First thing it does is it sets up the base pointer, saves the old base pointer. So I know it's a little confusing. You step through it, you'll see that the caller and the callee have to work together to construct the stack frame, and it has this recursive nature to it because every time you do the call, there's another stack frame construction. Okay, so that's what call does. Call sets up the callee's func's stack frame, starts setting it up. And then once it's done, what happens once the callee is done? So what happens to the stack frame when the callee is done? Yeah.
It pops up all the local values of the callee function, and then it updates the base pointer to the old.
Exactly right. So it tears down or like updates the stack pointer to remove the locals, and then it restores the old base pointer, pops off the old base pointer, sets the base pointer. And then it's done. It can return now because the green part was set up by the caller. So when you call return, the return function, so this is the end of the, this is the prologue. Let me put return value aside for a second. This is the epilogue. This is the part that tears down the stack. So we take the current base pointer and assign it to the stack pointer. Why do we do that? Why does that tear down the stack? So remember when we...
Is the function done?
What's that?
Is the function done?
The function's done. And remember, when we set the base pointer, we did it by assigning the stack pointer. So we just reverse that process. We just say, all right, the base pointer was actually the old stack pointer before we started pushing locals. So in order to tear down the locals, we just invert what we did in the prologue. The prologue copied the stack pointer to the base pointer. So we reverse that by copying the base pointer to the stack pointer. That now tears down the locals from the stack. And then pop will copy whatever data is on top of the stack, which is now our old base pointer. It's the reverse of push. So you can see here that we have push RBP and move RSP to RBP. This is the exact inverse. We move RBP back to RSP and then pop off RBP because we pushed it at the beginning. So it's the exact inverse. Remember, first in, last out. We invert this process. And what return does, return pops off the return address and jumps to it for you. So you don't have to handle that part. And then that goes back to the caller. Questions on that? Yeah.
It's for like recursion?
Well, this is for all function calls. Doing it this way ensures that each call has its own stack frame and allows for recursion to work as we expect. All right. Hopefully I've twisted your brains a little bit trying to reason through this. Once you step through it, it's not too bad, and you can just follow the assembly instructions. So one last point. Oh, yeah.
Okay, I was gonna ask about like if you want to return like the value, were you gonna go over that right now?
Return of value. Yeah, that's exactly what I was going to go to next. So the thing to notice here is that the return instruction is not like a return statement in C. Return statement both transfers control to the caller, but also sends a value to it. That's not how it works in the assembly world. The assembly world, all return does is pop off the address and jump to it. So if you want to pass a value, this goes back to the calling convention. The return value, by convention, is passed through a register. And so in our convention, this is in register A, RAX. So the return statement in our language is going to just set that register. It's not going to actually transfer control. It's just going to set the register. It's the epilogue of the function that transfers control.
And you have to ask a question like that. What happens, I know that RAX also has scratch register, which means it doesn't have to be preserved. Would that mean, what if both return registers were used? What would happen then? That's my question.
Oh, so only one return register will be used at a time. So yeah, if the caller wants to also use it, it's going to have to overwrite it once it's done with the return value. Yeah, so these are not like in parallel. They're like linearly called. So at least not in this framing. No, it's fine. All right, questions on that? Yeah.
Is anything done with the parameters stored?
So we'll go over parameters next week. It makes things a little bit more tricky, but all you really do is you have to add code here in order to copy the parameters to registers or push them onto the stack before the call.
Like the return, like that.
Oh, for the return.
Like
So the reason is the locals get handled by restoring the stack pointer, but the parameters were handled by the caller, so it's the caller that has to.
so once you return, then you're expected to deal with the parameters?
So this is the tricky part. So this shows both a call, and this shows both a caller and a callee. So once we'll talk about parameters, but basically you push parameters before the call and pop them after the call. That's how it's going to work. But we'll get there. We'll get there. Okay, so I think we kind of already went over the stack frame stuff. So let me give you a preview on let me go over the project first. So any questions on how this function calls work? Yeah.
Well, I was just going to ask more generally, like, is this concept, does it apply to like most systems, even though like, I know the registers and stuff are different, but
Yeah.
overall the concept?
Yeah. Whenever. Most systems will have an application binary interface, an interface for how to call functions between a convention that the compiler and the system will use.
But it does like the whole like stack frames and
Yeah.
pushing it.
Yeah, this is the classic way to do it for compiled languages to like machine code.
Okay.
Yeah, I mean, there's not a huge amount of diversity in like processor architectures these days, right? It's like x86 or ARM are probably the vast majority, at least for consumer devices. But I think even any and C is like all over the place. So this is the semantics of a C function, how a C function works.
Okay.
Yeah.
For that move instruction, so we put 10 into RAX, and then when we do return, we just
just get that value?
The caller will get that value. So you as the compiler writer, like when you write a function in C and you write a return statement, you don't care what the caller does, right? Like when you write the callee function, you don't have to consider how the caller is going to use it. You just return it. So it's the same thing here. You just set this value, and it'll be in the register when control is transferred back to the caller. And so it's up to the caller to handle this return function. We'll talk about that when we talk about like variables and calls next week. Or variables is in 2 weeks. All right, so that's the calling convention. Take some time to wrap your head around it. It's a short piece of code, but it's sort of dense how this actually works. All right, let me go over the project so everyone is at least ready to get started on it. So in this version of the project, all you'll have to do is compile programs that define functions and call functions. That's it. So let me give you a full example. So this is the most you're going to have to compile. Yeah. Oh, yeah, sure. So this is the most amount of constructs you're going to have to compile. You'll compile functions, function declarations, return values, and calls. And you won't even have to handle variable assignment. So the syntax of the language requires storing the return value, but you can ignore it for this project. Because I just want you to get generating this, prologue and epilogue and getting function calls to interoperate. And if you get this working, you'll actually be able to call C functions. You can actually write, and I'll show examples when we get to the full compiler. This is the same ABI that the C compiler uses, so we can actually call C functions, and C functions can call your functions because we follow this ABI. Yeah.
I assume like the code Gen 2 is going to build off of it.
Yeah, it will. So I'm assuming everyone's going to get CodeGen 1 right. I might be wrong. But the other ones, I have ways to be able to grade it without you getting every part right. So I tried to break it. So it's actually going to be like 4 separate repos. It's really gratifying, I think, to have a full compiler working. And you can do this if you like at the end and like combine it all together. But we're going to try to grade them separately. But yeah, the second one does kind of entail the first one. But I hope the first one is... What's that?
Monty, my taking system software, Monty, and he had all 4 of our program assignments built off of each other, kind of something like that.
It is, but it sort of penalizes you if you get the CodeGen 3 right, but you didn't get CodeGen 2 right. So they're divisible. They can be divided up. 1 and 2, you may have problems dividing it up, but I'll try to make sure everyone gets CodeGen 1 right. The code for it is pretty straightforward, but you have to understand the calling conventions for it. So the most you'll have to compile is programs that look like this.
Yes.
And you'll only have to do the call part. You won't have to save the variable. So you'll just have to compile programs that look like this. And then this is an example where we have 2 functions that one calls each other. So main calls func, and you only have to return constant values. And this is what the code looks like when you generate these programs. So this is generating main. This is generating func. So you can see that this looks exactly like the code that I just showed you. Actually, it is the same code that I showed you. All right, so to do this, without getting into the details of Antler, you only have 4 functions to write. And so actually I have the same example. So this assembly file metadata, you'll use the enter unit function. So I've given you this already. So you can just copy this template, this Python code. You can just copy this. Hopefully the indentation will work because this is text. And you only have to implement these 4 functions. Enter function, exit function, enter return, enter call. And I've given you a little mapping here between what parts of the assembly file correspond to which parts, which functions you implement them in. So enter unit is given to you. And this just, generates this code here. So notice here that it's, in Python, this is just writing to an out file. And this is just text. So keep in mind that the compiler is literally just generating text. It's not running anything. It's not computing a value. It's literally just read text and print text. So it's printing out this exact text that is in the the pseudo ops of the compilation unit. So for the function label, you'll do this in enter function. And the only thing that changes between programs is this name main. So you'll generate a string. Let's see how much I can't remember how much I gave you. So you'll generate a string, and in order to figure out what the name of the function is in the input program, you just use CTX name. So this is the part of the tree that holds the name of the function from the input program. And so you use that to fill in, to think of this as a template, where you just fill in the name of the function here. And then the prologue is identical for all functions, at least without local variables. It's the same for all functions, so you can just hard code this string being print out in enter function. Like, yeah.
So basically all functions we're doing, they're still just using strings. All we're doing is string out strings.
All you're doing is strings, yeah. So you'll literally you can just literally copy this, and you can check out you can kind of draw some inspiration from how this is done in Python. You can have multi-line strings in Python. And this is how you can insert a variable into the string. You use these curly braces. And I think I write this in the instructions as well. You can use these curly braces to do it. So this will just print, yeah. What's that?
It's like the F-string format?
It's like F-string, yeah. It's like F-string, except you can actually put the variable name inside. You don't have to do the whole like fprintf thing. So between curly braces, and note that you use these triple quotes to have a multi-line string, and this quote is actually being print out. So you won't have to use quotes in what you print out. But so what that means is you can actually just literally print this out. You know, the first step you can do is when you write enter function, you just literally say self.out file this string. I would do that first. If you get that working, you're already like a third of the way there. And then the only thing to do next is just to parameterize this part of the string here. You just say curly braces and then, ctx.name, because that gives you the name of the function for these three spots. And that's it. Enter function is done. And so now you have a compiler that will generate, for any function given, it'll generate the label of it and then code that will create the prologue. So in terms of a program, this is not that complicated, right? You just literally print out a string. It's the working out of the prologue and epilogue and the stack frames that is the complexity here. So exit function will run once you've, so it's, you only have 4 minutes, but it's basically a tree traversal of the simple IR tree. And then the exit function runs after you've seen all of the children of the function. So exit function, you just print out the epilogue. And this is just hard-coded. This epilogue is going to be the same for every function, so you literally just print this out to the file. Self.outFile.write, this string. And that's it. No parameterization, you just literally hard-code this string. Pretty simple, right? As a compiler, sort of. It's working out what you print out, that's the hard part. But the actual compiler itself is literally just printing text, just printing assembly text. So for calling functions, this is also pretty straightforward. It's just call factorial. So I've given you a little code to figure out from the tree which of the names is the function name. So this, I think I showed the IR a little while ago, the grammar of the IR. Where did I put this? And so you can sort of learn this as you go, but the way the grammar works is that the syntax of a call is some name for the variable to store, the assignment operator, the call keyword, a name of the function, and then 0 or more names of the parameters. Well, I'll go into this a little more next time when we have to do more complicated constructs. But in Antler, you can just pick out which of these names you want. You can just treat this as an array of names, which I give to you, and I tell you which index will contain which parts of the construct. So just run this code, write this code, and just use call1 in order to get the name of the function. And so in order to generate this, you literally just print out call and then whatever this name is. That's it to do the call. So return value is similarly simple. You just print out a move immediate to RAX. To get this value, it's the same idea. I've given you code to do this. You just use this CTX operand.text. Just use that variable, and you'll be able to get this number from the tree. We'll go into a little more detail next time about how the tree actually works, but if you just follow this schema, literally just print this out and then parameterize the text of the immediate value using cts.operand.text. So this code here, this CTX, this is just Antler's library for getting the text that's on the parse tree. That's all it is, and I'm giving you the actual Python object to use to get that text. But start out by just printing out the built-in text. Don't even worry about the parameterization yet, and see if you can get a working program that just literally prints out assembly for these 4 functions: enter function, exit function, call, and enter return. So these are the 4 functions here. So you have the actual assembly text to print out, and then once you get that working, parameterize it. Use the format string to have the function names that are for the call and for the definition. All right, questions on that in our last minute? So try it, ask questions next week in office hours, ask me next time in class. I hope that's pretty straightforward. I hope everyone will get this one. Yeah. Yeah, he did the project. Yeah, he's going to go over it. You gotta ask. Yeah, go to lab, and he will show you this as well. So I hope everyone will get this one. I tried to make this one pretty straightforward. So yeah. All right, everyone, have a good one.